Hello everyone, welcome to part 2A of Computation Methods Homework 2. Today we're going to be talking about the Secant and Newton methods for finding the root of a scalar one-dimensional function. So over here I have our Google Colab sheet from the initial 3 parts of this homework. And I made this new section for talking about the Secant and Newton methods. So what is the Secant method? So the secant method is essentially a root finding algorithm that essentially what it does is it uses these secant lines shown in this graph to approximate the root of a function f. And the way it does that is it uses this recurrence relation here where you can step up, get new x's for the function, and then solve for the function until the function equals 0 or very, very close to 0. And what we do is we use this here to, we use this to get new x's, and we use this to solve for it to see if our x values correspond to a 0. And we iterate that over and over and over until we get to a root. And then it'll stop at that point and give us the root. Okay, so start by defining our secant. And right off the bat, what we need is we need a first and a second initial guess x value, because this algorithm depends on having a starting point from which place to stop. So let's start by giving it a function, x0 and x1. Okay. And what we want to do is we want to solve for, that should be f0. We're going to solve right away for what the function equals at x0 and x1. So f1 equals x1. Okay. And the third thing we're going to do is we're going to want to make an array to capture all of these values in every iteration so that we can look at it later if we need to. So let's just call that xy list, should be next, equals, and then we'll make an array with x0 and f0, then x1 and f1. Okay. So now that we have our initial starting point and a place to put all of our values, what we're going to want to do next is make a for loop. So let's do for I in range. Now this is the range we're gonna do this over. We probably should give it a max iteration so that the thing just doesn't go on forever and ever and ever if it finds a function it can't find a root for. So let's do max iteration, and let's actually make that as a, let's just set the equal right here, and let's just do like 1,000. Okay, so now that we have our for loop, what we want to do is we want to first so now what we're going to do is we're going to define the next x value based off of those previous x values. So as you can see here, it's going to be our x2 is going to equal x1 minus f1 divided by x1 minus x0 over f1 minus f0. So let's do x2 equals, what's that? x1 minus, is that f1 times x1 minus x0, x1 minus x0 divided by f1 minus f0. Okay, So now we have that. Now let's solve for that. So f2 equals fx2. And then what we're going to do is we're actually going to append our xy list that we made. So we're going to do xy list dot append. And we'll do x2 comma f2. And here what we'll do is we'll check to see if our f2 is 0 or not. So we're going to do a break, or we're actually going to do an if f2 is less than, let's define a tolerance actually. So let's set tolerance equal to 1e negative 10. That's a sufficiently small number that if we solve for it, the answer would be pretty much 0. Okay. Now what we're going to do is we're going to reset our numbers here based off of the values we have now. So let's say x0 and f0 are the old x1 and f1 now become the new x0 and f0, and the new x1 and f1 are the old x2 and f2. Okay. Then what we'll want to do is we'll want to return x2, f2, and xy list. All right, I think that's all let me double check, but I'm pretty sure that's everything we need for this function here. Because what this function says is, given a function and two initial values, it'll iterate and iterate until our f2, the actual function itself, is less than 1e to the negative 10, which is pretty much 0. And what it'll do is it'll return our x2, our f2, so our final x, our final function value, and then the whole iterative list that it calculated for us. Okay, so that's the secant method. Now the Newton method is a little bit different. It's designed to do the same thing. That it's a root finding algorithm which, provides better approximations of the roots of the function. So, and in this one, we're going to assume it's a one-dimensional function. So one variable. So this one. So in this one, we're going to use this expression here to give for our iterative purposes instead of what we used in the secant method. And you'll notice the Newton method uses the derivative of the function at a particular end to get the next value, which will be important for us. So let's start by coding this piece right here. Okay. So this function will look very similar to the secant function that we calculated above, in the fact that we'll need a function, we'll need an x0, but noticeably, Newton's method does not need an x1 because you calculate for the x1. So you only need one initial value. So, and we'll do the same max iteration, set that at 100, and another tolerance equal to 1e, same tolerance. Okay. So first things we're going to do is we're actually going to solve for, actually, the first thing we should do is we should actually calculate the derivative of it. So the way we're going to do that is we're actually going to use the Jacobian, as we talked about homework 1, to solve for this. So let's call it f prime is equal to Jacobian of f solved at x naught. Okay, and what we'll need to do is we'll actually need to import that. Okay, let's get Jax. Now to do the Jax 64-bit. I always have to look this up. I can never remember it correctly. There we go. So actually, let's use the gradient. Make sure that is what I want. Gradient. Yeah. So since this is a one-dimensional function, we can actually use the gradient, and the gradient will actually be a little bit more simpler for us to use. So f prime is a gradient. Let's say f0 equals, well, the function at x0. And let's do the same xy list. And we'll start it with just x0 and f0. That needs a colon. Yeah, that needs a colon. Now, to solve for x1, as we talked about here, so x1 is going to be equal to x0 minus that f sub x. So x0 minus, what do we say it was? F of 0 minus f prime. So f0 divided by f prime at x0. Then we'll do that same append. Okay, we'll add x1 and f1. Okay? And we'll do an if check to see if it works. So we want to get in the tolerance. And what I forgot to do in the last one, which I'll do here, is you have to take the absolute value of your f1, because it could be on the other side. So the absolute value of it, if it's less than, well, you want to take the absolute value, because if your function overshoots and goes beyond 0, and you don't have the absolute value triggered, then it'll just break, because, you know, -1 is less than 1 e to the -10. So we want to do it this way. It's less than the tolerance. Need another colon up there. Then what we want is we want just to break out of this for loop. But if that is not the case, then we want to do what we did here and kind of reset our variables. So we're going to do x0 and f0 equal to our new x1 and f1. And that should get us to where we want to be. Oops, no, not you. And f1. Okay, so we're going to return x1, f1, in our xy list. Okay, so let's just fix this absolute value here. And these are the functions that we went ahead and calculated. So let's just check, make sure we got everything. So we coded these two methods, okay? So this is the secant method. Let's just do a quick conclusion. This is our secant method. It takes a function, two initial values, and it goes through this iterative process to calculate calculate new x's as our functions get closer and closer to 0 until it finally hits 0 and then it breaks. Now the Newton method, it does the same thing. It's an iterative process to approximate the 0 of a function. However, this one uses this gradient to calculate the derivative of the function as it goes along with each new x. And we use that derivative to get a better and better approximation of that 0 until we eventually hit the 0. Okay, so there. So that should get rid of all the errors. I don't see any more. Let's just run these to make sure that, okay, not giving us any errors. So join me in part 2B for the next section of this homework, where we will implement Newton's method for finding the root of a vector function. And that'll be a bit different because now we have more than one dimension that we're going to be looking at. So see you there.